Welcome, dynamics students. This problem is hearkening back to impulse momentum and application of impulse momentum principles to steady state fluid flow. And this problem is actually drawn from the Hibbler 14th edition textbook, problem 15129. And it's interesting because it brings up an application of our fluid impulse momentum and mass flow rate in a way that wasn't captured quite so well with our examples of reference volumes in the past, where we use these principles to look at a spout or a pipe or something like that, where we could take a little section of the moving fluid, look at it as our reference volume, and then basically treat it as something in a way as a statics problem, where we looked at the forces that would be generating the impulse necessary to change the momentum of the fluid moving through it. And because the fluid is moving with a mass rate, impulse being the integral of force over time, we could just say, hey, we know the mass rate, so instead of having an impulse, we actually have a force, and we can treat the whole thing like a statics problem. In this case, we have something that's a little bit different. Instead of having a reference volume, what we have, this is a fire hydrant, and we're given a couple of spigots where water is flowing into the hydrant, and then it's flowing out through a couple of these ports, but the water is flowing in, and I'll draw it in blue here. It's coming up all the way through the bottom. This entire bottom is coming in. Water's coming into it over its entire base, and we're given the area of that base. And then it's flowing out these orifices, and we're given certain dimensions of the problem. We're given, the height of this port is 0.6 meters, and we're given an angle that this has to the horizontal. I think it's 30 degrees. And then we're given this height as being 0.65 meters, so it's a little bit higher. Oops, 0.65 meters. And the reason that I wanted to demo this is it's a little bit different application of our momentum change and force impulse, where instead of having an entire reference volume necessarily and saying, okay, we're going to assume that all of the fluid in this volume is basically, its movement would be steady, and we're going to look at an average force across that entire reference volume, and it's going to act, somewhere along the walls. It's usually frictional transfer. This time we really have to start looking at the forces that are creating the impulse that's changing the momentum, the direction of the water flow, acting at points. So for that, one easy way to look at this is to look at the water inside the hydrant kind of as being stationary. It's got a pressure. It's like a pressure vessel, and it fills up, and it's got pressure, but it's not really moving. If it's not moving, it's got a zero velocity. So if we look at the water coming into the hydrant, and we're given a mass flow rate there, and I'll write this as in blue to remind us that it's flowing water. We got water flowing into the hydrant from below at 0.75 cubic meters per second. And we've got an area down there at point C. We're given a diameter from which we can calculate an area, and I'm just going to write down the area at C is a certain number of square meters, 1767 meters squared. And so from that we can get both a velocity of the water at C of 42.445 meters per second. And we can get a mass flow rate if we add the density of water as 1,000 kilograms per meter cubed. So we get a change in mass of the water at sea per given time. And this is, of course, our link to going from impulse to force, because we've got our time derivative kind of built into what we're going to use for a force expression and a change of momentum. So we have 750 kilograms per second of water flowing into the hydrant at sea. We're also given a pressure that we're going to encounter there. And we can just keep writing that. Maybe we can write this over here. We're told that the pressure there that's coming into the hydrant, and which would fill the hydrant, is 300,000 pascals or newtons per square meter. So that's going to be, we can look at pressure times the area, and that is going to be a force that would be lifting the hydrant up. So we can use that as part of our force balance in addition to our direction change. So the water's barreling into the hydrant at 42.445 meters per second and stops. It's got pressure in here, but ain't got no velocity. So we can look at a change of momentum expression for the water at Q coming in. It's got velocity in the j-hat direction. In fact, we could put a little coordinate system up here and start dividing up our directions. So we're going to have, we can give ourselves a vector direction here. And it's and when it gets into the hydrant, due to the action of the hydrant forces pushing down on it, it's going to stop. We're going to have pressure, but we're not, that velocity is going to stop. Now, we can use the same argument over here at our other points at B and A, and say we go from fluid that has pressure, but it's not, a little water molecule sitting right here. It's not going anywhere. It's just sitting inside the hydrant. And then when it moves from this point to right here, it gets a whole lot of velocity. Wow, change of momentum, force acting on it, action, reaction, and there we go. We've now got a force that we're going to use to set up for our statics problem. So this is, you can think of this as being a little bit different flavor of the reference volume argument that we use to get our momentum change due to the flowing fluid. We're still going to have a velocity and we're going to have a mass flow rate, but when we look at the force that's being applied at a given point, it's really easy to say, no, water's not moving inside this pressure vessel. It isn't flowing through it. I mean, it is flowing through, but once it's in here, any given water molecule is just kind of moving around. It isn't until it gets right up against the nozzle that it goes whoosh, kind of accelerates. Force is being applied. Impulse, force is being applied over time. Momentum is being changed in proportion to the rate at which the water mass is flowing out. Action, reaction, and then the rest of our impulse momentum arguments apply. So this allows us to look at basically a point application of the force that creates the impulse that changes the momentum with each increment of time and each increment of water that moves at steady flow. So that's why I wanted to demo this problem. It is using all the same principles, but it is ever so slightly different than the ones given in the Hibbeler text. And for reference, that this problem is Hibbeler 14th edition. It's problem 15.1. 129. If anybody wants to look it up, it's a little fire hydrant problem and it's pretty long. And I'm not going to necessarily go through all the calcs, but I'm going to try to hit all of the highlights here. So let's take a look over at A and see what's going on at A. We're told that the flow rate coming out of A is, we're told that the flow that comes in is splits evenly between A and B, so we can divide our 0.75 cubic meters per second in half, and so we know that at A we've got 0.375 cubic meters per second, and we know the area at A and B. Area at A, we're given the diameters of the orifices so we can get the areas. So the area at A is 4.418 times 10 to the minus 3 square meters. So that means we can get the velocity at A, which we know is going to have a component in two different directions. So we're going to start with just the magnitude of the velocity at A, which is going to be our Q of A divided by A of A. But we can resolve that into 42.440. Hey, there's a familiar number. Meters per second. J hat, it's going up, minus 73.508 meters per second I hat. So we've got two components of velocity at A, and we can calculate a mass flow rate at A, again using Q and A and density of water. And that's 375 kilograms per second. And last but not least, we can do the same thing with B. We've got the same QB is QA. We'll just say QB equals QA. And I believe the area of B is the same as the area of A. So from that we can calculate, basically we're going to have the same mass flow rate. We can just say this equals dmB dt. And so the velocity of B, and we're going to give it a vector direction, is going to be 84.9 meters per second I hat. So from the standpoint of calculating our momentum impulse, things we need to know for each of these different points, we're going to have an MV, which is going to be, here's our mass flow rate, so that's our time rate, our mass flow rate, so there's our m per unit time, so the m part of our momentum. And then we've got, in this case, we have incoming velocity, which then stops. So our change in velocity at C is going to be negative 44.45 meters per second. At A, we can look at our velocity as having been 0, a little packet of water just sitting here, and then it shoots through the nozzle, and it's going to acquire this velocity. So we can look at, it's going to get a positive change in the J hat and a negative change in the I hat, and it's going to be associated with this mass per unit time. And then likewise, here's our velocity change is going to go from 0 to almost 85 meters per second at B, and we're going to have that same mass flow rate. We're going to have it 375 kilograms every second, giving us that linear momentum change from 0 to almost 85 meters per second times our mass flow rate. Okay, so if we want to look at force, we're going to start tallying up our forces on the hydrant. I'm going to do that in green. Now we're going to apply impulse momentum, and we're going to start with the force on the water. I'll just say on H2O for water in the y direction, and we're going to just start tallying up impulses, or excuse me, tallying up changes in momentum to get impulse per unit time, which is the same as force. So we're going to start with A. And then we got our changes at B and VBY, which is 0. VCY. And in the case of the y direction, we've also got the effect of, we're going to have the effect of pressure, which times the area at C, which is going to end up being 21.2 kilonewtons in the J hat. Sorry. So if we take these one at a time, sorry, needs to be in minus sign. Oops. On the water. So we end up getting 15.9. Pardon while I pause for calculations and referencing my calc sheet. We have no y velocity going from 0 to anything in the B direction. It's shooting out straight horizontal, so that term gives us 0. And then in the case of C, we've got a negative. We're going from a positive y velocity to stopped. So if we multiply by the mass flow rate, we're going to end up with 31.8 e to the third newtons. We add in the effect of our pressure of our 21.2 kilonewtons that is having to be pushed down on the water, and we end up getting a total y force on the water of negative 15.9. Oops, sorry. We gotta take a quick pause while I get some figures straightened out. I've got an error here. I'm going to correct it and get right back to you. Okay, here we are back having our calc error corrected. It turns out the pressure are 300,000 pascals, and our area at Q gave us 5.3 kilonewtons, or 5.3 times 10 to the third newtons. So that's this final term. It turns out they all add up to 21.2 kilonewtons. So I was reading my sums wrong. So again, this is basically the force on the water from the hydrant. So we can say that the sum of the forces on the hydrant, we're going to use action-reaction in the y, can be given by basically flipping them. If we have to exert 15.9 kilonewtons in the y direction on the water at A to get it to shoot upwards out of the nozzle, that means it's pushing downwards on the hydrant 15.9 kilonewtons. And we got nothing going on at B because we are not changing the direction of the water at B. At C, we have water that, we're basically having to exert a downward force from the hydrant to change the velocity of the water from its upward 42.45 meters per second to stopped inside the hydrant. So there's going to be an upward force coming from that on the hydrant. So we end up adding that, 31.8 kilonewtons. And then the pressure force again is going to be upwards on the hydrant coming from the water at this base. So it's basically an upward force. So that ends up getting added in. So it combines with the water on hydrant force at A at the orifice in the upward direction. So that adds just another term, and it all sums up to 21.2 kilonewtons upwards. So that's our J hat force water on hydrant. We can go through completely analogous calculation for our X direction. We can look at the force of the water, force on the water by the hydrant to get the water to change direction in the X. And we can look at that at both points, or we can look at it at all 3 points, and some of them are going to be 0. So we can start with X. So we've got our change in mass flow rate at A, or our mass flow rate, sorry, not the change in mass flow rate, because we're at steady state. There is no change in the mass flow rate. It is constant, but mass per unit time, not mass, not change in flow rate. So we have VAX plus what's going on, our change in momentum is a good way of saying what this product is, VBX plus, in this case, we could say the same thing with C, but we know that there is no X component. We could say VCX is going to be the force on the water in the X direction. Pressure doesn't factor into this one in this case, and we know that VCX is 0, so we simply get the force exerted on the water by the hydrant to accomplish this change in momentum. We can say that at X, basically the water is going to go from 0 to some negative velocity. It's shooting in that negative X direction. So we're going to end up with a negative 27.6 kilonewtons. And then in the case of B, it's going to go from 0 to that positive 85 meters per second. That when we multiply by the mass flow rate, we should get 31.8 kilonewtons. So again, action reaction, if we look at the force of the on the hydrant from the water in the X direction, we just add those two and flip the signs. So we end up with 4.2 kilonewtons. So it's going to basically be it'll be in the negative direction, net. We're pushing it over to the left. Okay, moment. I'm going to clear a little bit of space here. And here's where having the dimensions of the hydrant and the knowledge that those changes in momentum at the orifices can kind of act like point forces, we can end up looking at the hydrant as a statics problem and saying that we can look at it from the point of view of having, can FBD the hydrant now and say that we have force at B, and we've got resolved force AX, force AY. If we took the moment about point C, dead center, in the hydrant, where we don't have to, pressure forces and the force due to the momentum change of the water coming in at C aren't going to factor in because they're effectively they're going through point C. Basically, we can just look at basically doing our R cross F, RCB, to our points of application and just calculate the moments the way we would in statics. So we could say the sum of the moments about point C. We can just break up those vectors, calculate each one based on their perpendicular distances, and we end up getting negative 15.9 kilonewtons times 0.25 meters. And that 0.25 meters was coming from a dimension here. And then we have 27.6 kilonewtons times our 0.65 meters here. So that's basically getting this force, that force, the moments about point C due to those, given their radial offsets. And then of course we have B, and it's going the other direction. So we have negative 31.8 kilonewtons, which is the force that is being exerted by the hydrant, or on the hydrant by the water, in order to change its direction and get it moving out the nozzle at B. Take a parentheses off there because this is just an operation, not a sign. Minus 31 kilonewtons times our 0.6 meters. And that ends up being 5.12 kilonewton meters being exerted down at the base. So that's how you step through the application of impulse momentum for a steady flowing fluid, where it's flowing into a reference volume that's really not a flowing reference volume, it's a container. And I would call this basically a pressure vessel. So it flows in, stops. There is an applicable pressure at a given plane that, if it's given, we can look at its effect on force in a given direction. But you can look at those velocity changes as you have a velocity coming in, it stops, and then you look at the other orifices and imagine a water particle stopped and then accelerating due to a force being applied over time based on the mass flow rate to achieve its new velocity and hence its new momentum. And then that new momentum, of course, is granted via our impulse per unit time given by the mass flow rate, and boom, you have your force. So all you really need to do is know the mass flow rate at each orifice, the velocity change to go from stagnant inside the vessel to whatever the velocity is when it's shooting out of the vessel, which you can get again from the flow rate and the orifice diameter and the density of water. You have everything you need to know for localized application of forces. Again, if you're talking about a reference volume and an elbow or a pipe, you've got to assume that that force is being applied maybe uniformly along the walls of the pipe or the elbow, and so you'll look at that entire coupling or pipe as having a force acting uniformly on it, maybe at its centroid typically, in its orientation. And again, that's very similar to the example given in the Hibbler 14th edition text. But in this case, the water comes in, you can kind of think of it as stopping. So wanted to give that as a clarification because it is a little bit different, and it's kind of an interesting problem with a very practical application for any of you who are going to go into water systems design. Those flow rates are typically specified by law. So being able to specify the correct fixture with the force necessary to handle those flows, those minimum fire flows they're called. This is a fire hydrant. It's very important to know what to buy. So that is it for this mini demo, and see you for more examples moving on into rigid body motion.